Longitude and latitude lines on the Earth form a grid system which has been used by geographers for centuries to define locations on Earth by referencing their particular coordinates in longitude and latitude. Latitude lines are often referred to as lines of parallel, as each latitude refers to an angular measurement between the equator and the poles. Thus, all points on the Earth 10 degrees north of the equator make a circle about the Earth known as 10 degrees north latitude. All points 20 degrees north of the equator make a circle about the Earth known as 20 degrees north latitude. And the 20-degree circle is parallel to the 10-degree circle. On this latitude grid, there are 5 great circles that have astronomical significance. We have already mentioned one, the equator. The other 4 are the tropics of Cancer and Capricorn, and the Arctic and Antarctic circles. Let's start at the middle and work our way from there as we discuss these 5 great circles of the Earth. Earth's equator is located at 0 degrees latitude and cuts the Earth into an equal northern and southern hemisphere. While there are many geographical and climatological significances to the equator, there is one very special astronomical connection to the equator. Each year, on the March and September equinox dates, the sun rises and sets on the eastern and western horizon respectively, directly above the equator. And during the day on the equinox dates, the sun's daily path across the sky will keep it directly above the equator. No other location on Earth can boast to have this special connection with the sun's path across the daytime sky. About 23.5 degrees north of the equator is the great latitude circle known as the Tropic of Cancer. While the precise latitude measurement of this line does change over time, it is safe to say that the Tropic of Cancer lies approximately 23.5 degrees north of the equator. The astronomical significance of this measurement should be apparent to anyone who understands the causes of the changing seasons on Earth. Earth's equator is inclined or tilted about 23.5 degrees off Earth's orbital plane. What's so special about the Tropic of Cancer? The answer has to do with the ability to see the sun directly overhead when the sun is at its zenith or highest point in the sky. The Tropic of Cancer marks the most northerly latitude on Earth, where the sun can be seen directly overhead when it is at the zenith or highest point of the sky. The equivalent latitude line 23.5 degrees south of the equator is known as the Tropic of Capricorn. Any point between these two extremes will experience 2 days a year where the sun will be directly overhead when it is at its zenith. No location on Earth outside of these 2 great circles will ever see the sun directly overhead. On the tropics, the sun will be directly overhead only on the solstice dates. On the June solstice date, the sun, at its zenith, will be directly overhead on the Tropic of Cancer. On the December solstice date, the sun, at its zenith, will be directly overhead on the Tropic of Capricorn. The names of these tropics come from their respective constellations. 3,000 years ago, the sun was in the constellation of Cancer on the June solstice, and in the constellation of Capricorn on the December solstice. This is no longer the case due to the precession of the equinoxes, but that's a discussion best left for another time. The last 2 great circles of latitude on the Earth are the Arctic and Antarctic circles. The Arctic Circle is in the extreme northern hemisphere near the North Pole, and the Antarctic Circle is in the extreme southern hemisphere near the South Pole. Can you guess how many degrees away from their respective poles each of these circles lie? That's right, 23.5 degrees. The Arctic Circle is approximately 23.5 degrees south of the North Pole, or at latitude 66.5 degrees north. And the Antarctic Circle is approximately 23.5 degrees north of the South Pole, or at latitude 66.5 degrees south. The astronomical significance of these 2 circles also has to do with the position of the sun. During Northern Hemisphere summer, an observer at the North Pole will see 24 hours of sunlight every day, from the March equinox to the September equinox. The sun simply appears to move in a circle around the horizon, getting a little higher in the sky from the March equinox date to the June solstice date, then dropping lower in the sky from the June solstice to the September equinox. At the South Pole, an observer would see the sun circle the horizon on the September equinox date and would experience 24 hours of daylight every day until the March equinox date of the following year. So, at the poles, we have 6-month periods where we see the sun continuously. As we move farther away from the poles, that number of 24-hour daylight days decreases. Practically speaking, there are several days before and after the solstice dates where part of the sun will still be visible all night long. But it is on the Arctic and Antarctic circles that there is only one day a year when the entire disk of the sun is visible for a 24-hour period, the June solstice in the north and the December solstice in the south. The seasons. To the inhabitants of Earth's temperate mid-latitudes, they are just a part of life, familiar and, for the most part, constant. The new growth and sweet fragrances of spring, the warmth and long daylight hours of summer, the vibrant colors of fall, and the crisp chill of snowfall in winter. But seasons are not the same everywhere on our planet. In many tropical areas, there are only 2 seasons, rainy and dry. In the polar regions, it seems to be winter all year round. And close to the oceans, the seasons take on different characteristics. Why? As with almost everything else on Earth, the seasons are controlled by the sun. Every second, the sun pours vast amounts of energy into space at a rate that is virtually constant, and it has done so for millions of years. When the sun appears directly overhead, its energy provides the equivalent of a 100-watt light bulb plus one 25-watt light bulb over each square foot of ground. But because of Earth's spherical shape, the sun's energy is not distributed equally over the surface. If we were to take a giant strip of photographic paper and lay it on Earth's surface from pole to pole, we would find that while the incoming solar radiation, called insolation, measures full intensity at the equator, at the poles it drops literally to 0. This explains why the poles are so cold and covered with ice, but it doesn't explain the change of seasons. If Earth's equator were aligned with its orbit around the sun would always appear directly overhead at noon on the equator. But Earth's equator isn't aligned with its orbit. Instead, it is tilted nearly 23.5 degrees. Because it spins on its axis, the Earth is like a giant gyroscope, its poles always pointing the same direction. On one side of its orbit, the North Pole tilts 23.5 degrees away from the sun, and the South Pole tilts the same angle toward the sun. This happens on or about December 21st every year and is called the winter solstice. But on the other side of its orbit, the North Pole tilts 23.5 degrees toward the sun, and the South Pole tilts the same angle away from the sun. This happens on or about June 21st every year and is called the summer solstice. If we use another giant strip of photographic paper, we see something different than before. When the sun was aligned over the equator, the insolation was highest at the equator. But in June, insolation is highest 23.5 degrees north of the equator. This is called the Tropic of Cancer, or the Northern Tropic. And in December, the sun appears overhead at 23.5 degrees south of the equator. This is called the Tropic of Capricorn, or the Southern Tropic. It's almost like moving Earth's equator, and the resulting increase in temperature and the pole of the Earth's other hemisphere, with the resulting decrease in temperature to the north at the winter solstice. It is this annual change of insolation that causes the seasons. There are also a few minor influences on Earth's seasons. The first of these is atmospheric circulation. Caused by differential solar heating of Earth's atmosphere combined with our planet's rotation, these vast masses of air stir the temperatures, causing warmer tropical air to move toward the pole and cold polar air to be pulled toward the equator. Perhaps the most dramatic manifestation of this is seen in hurricanes, also called cyclones, which occur as part of the annual cycle of the seasons. The second of these minor influences on the seasons is oceanic currents. Similar to atmospheric circulation, these currents carry warm water from the tropics toward the poles, exchanging heat and humidity with the atmosphere and moderating coastal temperatures. Another of these minor effects is the tiny variation in Earth's orbit around the Sun. This variation is just over 3% of the distance from Earth to Sun and brings our planet closest to the Sun shortly after the winter solstice. This variation causes winters in the northern hemisphere to be fractionally warmer than in the southern, and summers in the northern hemisphere to be fractionally cooler than in the southern. Finally, there is one more change which also takes place as a result of the tilt of Earth's axis. Earth rotates on its axis every 24 hours. In the spring and fall, the Sun will momentarily align with Earth's equator, making the length of day and the length of night 12 hours each. This happens on or about March 20th and is called the vernal equinox, and 6 months later, on or about September 20th, and is called the autumnal equinox. But as our planet approaches solstice, daylight hours in one hemisphere increase, with night hours decreasing equally. In fact, above the polar circle, daylight consumes the entire 24 hours, leaving no time for night. In some parts of the world, this is called the land of the midnight sun. In the other hemisphere, daylight hours decrease, with night hours increasing equally. Above the polar circle in that hemisphere, the Earth descends to 24 hours of night with no daylight at all. As Earth continues its orbit approaching the other solstice, daylight and night hours change, favoring the other hemisphere.
Those that visit or live in coastal regions have the opportunity to observe the rhythmic rise and fall of the sea that we call the tides. What is responsible for this ever-repeating cycle of advancing and receding water? Tides result from the interplay of gravitational forces from the moon on Earth, the sun on Earth, and Earth's daily rotation. To better understand how gravitational forces produce tides, a thought experiment will help. Imagine that we place a number of masses in a circular pattern high above Earth and allow them to fall in response to Earth's gravity. What will happen as they fall? First, let's consider these two masses, one directly above the other. Since the lower mass is closer to Earth, the gravitational force acting on it is slightly larger than on the other mass. As they fall, the distance between them increases. Next, consider these two masses side by side. Gravitational forces pull objects towards Earth's center. Therefore, as they fall, they move closer together. As all of these masses fall together, their original circular pattern becomes oval in shape, stretching vertically and compressing horizontally. The gravitational interactions that result in this vertical stretching and horizontal squeezing are known as tidal forces. When an object such as a satellite, moon, or planet is in orbit around another object, its orbit is the result of two separate motions. One is a sideways motion at constant speed, and the second a falling motion towards the object being orbited. The sideways motion results from the object's inertia and does not affect the falling motion. Thus, the tidal forces act on objects in orbit. But how is Earth falling? We normally speak of the Moon orbiting Earth. In reality, both Earth and Moon orbit around their common center of mass. The center of mass is the place where the objects would balance if they were on a teeter-totter. The center of the mass of the Earth-Moon system is actually within Earth, about 3/4 of the distance out from the center. As Earth falls towards the Moon, tidal forces cause surface water to flow into an oval shape around Earth. There are two regions on our Earth that have higher than average water levels. They are towards and away from the Moon. There are also two regions that have lower than average water levels. These are at right angles to the Moon. As Earth rotates under these tidal bulges, locations on Earth experience high and low tides over the course of a day. If Earth were a perfect sphere covered by an ocean of uniform depth, high tides caused by the Moon would be 14 inches higher than average. Low tides would be 7 inches lower than average. Local geography, such as the shape and size of a bay, can either greatly amplify or nearly eliminate the rising and falling of ocean water. In one particular location, the Bay of Fundy in Canada, the water level variations exceed 30 feet or 10 meters. Tides are also produced by Earth falling around the Sun. Solar tidal forces are about half as strong as tides generated by the Moon. At full and new moon, solar and lunar tides reinforce each other. These larger than average tides are called spring tides. At first and third quarter, solar and lunar tidal forces work against each other. These are known as neap tides. Other complications, such as the geometry resulting from the tilt of Earth's axis, can also vary the height of successive tides at a particular location. So, if you enjoy watching the rise and fall of the sea or enjoy the variety of life that flourishes with the ebb and flow of ocean water, look up and thank the Moon.